In this video, we're going to start our study of conservation of momentum, and we'll specifically be looking at one-dimensional collisions. Let's think about the types of problems that we've looked at up to this point in the course. Either we've looked at problems that involve the motion of just one object, or when we've had multiple objects moving, they're always moving together in some way, as the example of the two blocks on the slide show. So even though it's two objects moving, we know that if this object is moving down the incline, this object is moving straight up. So their motion is linked. What we want to do now is allow objects to move independently from each other. And of course, if objects are moving independently of each other, then those objects can collide. And so the primary thing we're going to be looking at in this video is collisions. We're going to define a new quantity today, which is linear momentum. So linear momentum is defined as the product of the mass and the velocity. As we know, because mass is a scalar and velocity is a vector, it means that momentum is a vector. And notice the direction of the momentum always has to be exactly the same as the direction of the velocity. Looking at our definition of momentum, what are the units of momentum? Well, we can see that it's just the units of mass, kilograms, times the units of velocity, meters per second. Momentum does not get its own unit, so we're always just going to use kilogram meters per second. Now you may wonder where the concept of momentum comes from. Why did we define it this way? Why didn't we define momentum to be, I don't know, v over m or v squared over m cubed? Why did we come up with m times v? Well, it turns out, as we're going to see, that it really just comes from Newton's second law. This is actually not really a new concept. It's just looking at Newton's second law in a slightly different way. It turns out that the way Newton actually wrote his second law was not in terms of the mass and the acceleration. He wrote it in terms of the momentum. Newton said that when a net force acts on an object, that net force is equal to the rate of change of the momentum of that object, where he defined momentum as m times v. So the first thing that we probably want to do is just make sure that the version of Newton's second law that we've been using all semester is equivalent to the way Newton actually wrote it. So let's go ahead and take a look at that. So we've got the net force is equal to the rate of change of the momentum. And what I'm going to do then is just rewrite that as the derivative of what momentum is, which is mv. Now you'll notice that as long as the mass is constant, then the mass can come outside of that derivative, and we're left with m times dv dt. And of course we know that dv dt is the definition of instantaneous acceleration. And so we do get back to F net equals ma. What I want you to notice, though, is that when we write Newton's second law in this way, it's actually a special case of the more general version of Newton's second law. In other words, this is only true if m is constant. So if the mass of the object isn't constant and we're studying its motion, then we can't use that formulation of Newton's second law. We have to go up here because now both m and v can be changing. If you think back to all the problems we've done, you'll notice that every single problem we did, the mass of the object was constant, and therefore we were perfectly fine using F net equals ma. So let's look at why this concept of momentum is so important. The reason that momentum is an important quantity is that momentum is conserved in collisions. So here on the slide I say when the net external force on a system is 0, the total momentum of the system remains constant. And you'll notice that if F net is equal to 0, then it's simply telling us that the total momentum isn't changing. When I use a capital P here, I'm referring to the total momentum of all the objects that are moving. So let's see how this applies in a collision. Here we've got two objects that are coming towards each other, object 1 and object 2. And they're going to collide here, and then they're going to move off from each other after the collision. Let's concentrate on what's going on when those two objects collide. You'll notice that from our previous study of Newton's third law, we know that object 1 is going to exert a force on object 2 in a direction to the right. We also know that object 2 is going to exert an equal and opposite force on object 1 to the left. So in other words, from Newton's third law, we know that F21 is equal to negative F12. And again, we do want the minus sign in there because we've got vector signs over the F's. So the magnitude of F12 and F21 is the same, but obviously their direction is opposite. Well, now let's look at what Newton's second law tells us about what happens to each of these objects during the collision. If the only force acting on object 2 is this force, and the only force acting on object 1 is this force, well then we can make some conclusions. Notice object 1, if we look at what's going on for object 1, the force that's exerted on object 1 is F21, and that's got to be equal to the rate of change of object 1's momentum. For object 2, we know that F12 has to be equal to the rate of change of object 2's momentum. But notice that because F21 and F12 are equal and opposite, what that implies is that the change in momentum of our two objects is equal and opposite. In other words, if object 1 gains 10 kilogram meters per second of momentum, well then object 2 had to lose 10 kilogram meters per second in the collision. And what we notice then is the overall momentum, the total momentum, doesn't change. So that's where the concept of conservation of momentum comes from. It's really just an application of Newton's second and third law. Remember that when we say a quantity is conserved, like when we talked about conservation of energy, we simply meant that if you added up all the energy before something happened and compared it with all the energy after something happened, you'd get the same value. And that's exactly what we mean here with momentum. We're going to go through a notation change now, and up to this point in the course we've used naught to mean initial and nothing to mean final. So in other words, there's our old notation, v naught equals the initial velocity and v equals the final velocity. At this point, because we're going to have multiple objects moving at multiple different velocities, we're going to change that a little bit. So here is our new notation. Now there are a couple things I want you to notice. Notice that now we're using numbers to refer to which object we're talking about. And we're using I and F to mean initial and final. So in this diagram, object 1 would have a velocity v1 initial, object 2 would have a velocity v2 initial, and then after the collision, v1 would have a velocity v1 final, and object 2 would have a velocity v2 final. You'll also notice that I'm keeping vector signs on our new notation, whereas we didn't need it on our old notation. The reason for that is we're not always going to be able to predict what direction an object is going to go, and so we're going to need the math to tell us that. And so in order to do that, we have to keep the vector signs on the velocities. So in other words, whether this object is moving to the right or to the left, I can refer to its velocity this way. I don't have to say whether it's plus or minus because the directionality is contained in the symbol. We'll do some examples and I think that'll become a little bit more clear to you. But do make sure that you include those vector signs on your velocities. So how do we use conservation of momentum to solve collision problems? It's basically pretty straightforward. We set the total momentum before the collision equal to the total momentum after the collision. So let's see what exactly I mean by that. Here are two objects. Let's say object 1 is moving to the right, and again we're going to call that's the initial velocity v1 initial with a vector sign. Now for these two objects to collide, object 2 could actually be moving in either direction, right? It could be moving to the right as long as its velocity is less than v1 initial. But for the moment, let me just draw it this way. So that would be v2 initial. And then after the objects collide, you can imagine they could both go to the right, they could both go to the left, or they could go in opposite directions. Again, we're not actually going to know until we do the math for a particular problem. But I'll just show object 2 going to the right, so that would be v2 final, and object 1 going to the left, and that would be v1 final. And again, we're putting our vector signs on. Now, unlike when we did force problems and we put in by hand whether a force was to the right or to the left or up or down, we're not going to do that here. Instead, we're going to keep the vector signs on. So conservation of momentum, I'm always going to start and just write capital Pi equals capital PF. That's just saying that if you add up all of the momentum before the collision, it's equal to the sum of all the momentum after the collision. Now, how would I actually write that out as a formula that I could then solve? Well, now I'm simply going to add up the momentum before the collision. The momentum of object 1, since we know in general P is mv. The momentum of object 1 is just m1 v1 initial with the vector sign over it. Now I want to add the momentum of object 2. That would be m2 v2 initial, again with a vector sign. Notice I didn't put in a minus sign there because I don't actually necessarily even know what direction that object is moving initially. Same thing after the collision. The vector sum of the final momentum is just m1 v1 initial, or sorry, m1 v1 final plus m2 v2 final. So that's how I would write conservation of momentum. And again, the vector signs are important. Okay, let's actually do an example. Here it says two objects collide as shown. What is the final velocity of object 1? So notice that we've been given the mass of the two objects, we've been given the initial velocities of the two objects, and we're looking for the final velocity of object 1. Notice, by the way, that v1 is positive, v1 initial, and v2 initial is negative. So our drawing is correct. Object 2 is moving to the left, object 1 is moving to the right. After the collision, we can see that we know v2 final is positive, so that velocity is definitely that way. But we don't necessarily know whether object 1 bounces off or whether it actually continues in the same direction. So let's go ahead and solve this. Again, our first step is to write capital Pi equals Pf. You're showing me that you understand that fundamentally what we're doing is we're setting the momentum before the collision equal to the momentum after the collision. Now I'm going to write it out with vector signs. Before the collision, both objects were moving, so I have m1 v1 initial plus m2 v2 initial, and that's got to equal m1 v1 final plus m2 v2 final. Again, everything is a plus sign because I have the vector symbols over the velocities. I'm now going to solve for v1 final algebraically, and I'll just do that in one step. v1 final is going to be equal to m1 v1 initial plus m2 v2 initial minus m2 v2 final divided by m1. So at this point, we're now going to plug in the values, and that's when we'll find out whether v or whether object 1 is moving to the right or to the left. So v1 final is equal to m1, which is 2, times v1 initial, which is 5, plus m2, which is 4, times v2 initial, which is negative 5. So now's where the minus sign goes in. And then minus 4 times 1.67. And I want to divide that by the mass of m1, so divide by 2. If you work out the math, what you should find is that v1 final equals negative 8.3 meters per second. So we found, by solving the problem, that the final velocity of object 1 was to the left. It could very easily not have been, and you'll see many problems where, again, you won't know which way it's going to go, which is why we have to keep the vector symbols on and then see whether the quantity comes out positive or negative. Let's look at another example. In this example, the two objects collide and stick together after the collision. So again, we've got object v1 initial, or velocity of object 1 is v1 initial. We've got v2 initial. Now again, those objects don't have to be moving towards each other for them to collide, because obviously if one is going faster than 2, even if they're both going to the right, they would still collide, and the same thing if they're going to the left and 2 is going faster than 1. So I'm just going to say, I don't even know, I'm just kind of finding the general solution. In this problem, we're told that they stick together after the collision. In this case, I only need one final velocity, and so in a problem like that, I'm just going to write VF because the two objects stick together. So how would I write conservation of momentum? Again, I would start out saying that the total momentum before the collision is equal to the total momentum after the collision. And now I'm simply going to write down what is the sum of the momentum before and after the collision. Before the collision, most generally, both of them are moving. So I'd have m1 v1 initial plus m2 v2 initial. Notice that whether they're both moving to the right, both moving to the left, or moving towards each other, it doesn't change the way I write that. Then after the collision, I only have one object. They're stuck together. My object now has a combined mass of m1 plus m2, and I'm multiplying that by that final velocity. So that's how I would write down conservation of momentum in a problem like this. Let's look at an example. A railroad car initially at rest is struck by another car moving 24 meters per second. Assuming that the stationary car has twice the mass of the moving car and that they stick together after the collision, how fast will they be moving? You may want to pause the video and solve it yourself. Try to write it out the correct way and then restart the video and see how you did. All right. I'm going to first of all label the cars. That's going to be car number 1 and that's going to be car number 2. And so let's go ahead and identify what we know. We know that car number 2 is initially at rest. So V2 initial is equal to 0. We know that V1 initial is equal to 24 meters per second. So car number 1 is coming towards car number 2, which is at rest. By the way, one thing you might not know about railroad cars is they automatically couple when they hit each other. And so it's actually a good example of two objects that collide and stick together. Let's see what else we know. We're told that the stationary car has twice the mass of the moving car. In other words, we know that m2 is equal to 2 times m1. And we're going to need that because you'll notice I didn't give you the actual mass. Now that we've identified everything, we're going to call the final velocity just VF since there's only one. And I'm now going to write down conservation of momentum. So as we just looked at generally, we know PI is equal to PF. And so in this case, I've got M1 V1 initial plus M2 V2 initial is equal to M1 plus M2 times V final. Now there's no mystery about what direction the two trains are going to be going in after this collision. We know it's going to be positive. So now I can go ahead and solve for V final. Probably makes sense to just go ahead and cancel out the momentum of object 2 before the collision since it's not moving, but it's nice to put it in there. And therefore I get that V final is equal to M1 V1 initial divided by M1 plus M2. Now, because I know that M2 is 2 times M1, you'll notice that the denominator is going to simplify to 3m1. In other words, m1 plus 2m1 gives me 3m1. Once I find that, I can cancel out my m1s, and I get 24 divided by 3, or 8 meters per second for the velocity of the combined railroad cars. One of the things that we haven't talked about yet is that conservation of momentum not only works for collisions, but it also works for explosions. In other words, when we have an object that breaks into multiple objects, momentum will also be conserved. And that's again because there are only internal forces acting, action-reaction pairs, so the overall net force on the object is still going to be 0. Here's an example of where this happens in nature. This is called alpha decay. The nucleus of a uranium atom will spontaneously break into two pieces. It will actually throw out a helium atom and a thorium atom. And so that's an example in the real world where this occurs. Let's see how we would model this explosion. So we start out with one object, and that object is going to break into two pieces. That object might have some initial velocity, so most generally it could have an initial velocity, which I'll just call VI. And then after the explosion, there are going to be two final velocities. We're going to have V2 final and V1 final. Now, in terms of the direction of V1 final and V2 final, again, that would all depend on the relative masses and what the initial velocity of the one object was before the explosion. So we can't necessarily predict that, but let's write down what conservation of momentum would look like in this example. Again, we're always going to start with PI equals PF. And if we look at the momentum before the explosion, we had one object of combined mass m1 plus m2 times the initial velocity vi, and that's got to be equal to the momentum of object 1 after the explosion plus the momentum of object 2 after the explosion. So that's how I would write conservation of momentum in this kind of a problem. Let's look at a similar kind of example. A 71 kilogram astronaut, and that's the mass of the astronaut and the jetpack, is floating in space with a velocity of 2 meters per second. She fires 1 kilogram of gas from her jetpack at a speed of 200 meters per second in the same direction she is moving. What's her final velocity? Well, first of all, if she's shooting her jetpack in the same direction she's moving, she's clearly trying to slow down. Maybe she's even trying to reverse her direction. So let's figure out how successful she is at that. Let's draw the before picture. So here's my astronaut. She's got her jetpack on, and she's got a gun to control what direction the jet goes. And then afterwards, she has the same setup, but now some of the gas she's fired off, and that's moving off in the direction that she was initially moving. I'm going to call the initial velocity of the astronaut plus all the gas in the jetpack just VI, because we've only got one object. But then afterwards, we'll call her velocity V1 final, and we'll call the velocity of the gas V2 final. Notice that what that means is that the mass of just the astronaut after she shot the gas, that's what I'm going to call M1. So that's going to be 70 kilograms. And M2 is going to be the mass of the gas that was shot, which is 1 kilogram. Okay, so let's go ahead and solve this. We can see that the first thing we want to do, because it's what we always want to do, is write down that Pi equals Pf. The total momentum before she shoots the gas and after has to be the same of that system of her and the gas. And again, the reason that has to be true is they're only internal forces. Whatever force her jet gun exerted on the gas exerted back on her jet gun. So the net force on her and the gas as a system is 0, so the total momentum can't change. Initially, everything was together, so we had a combined mass of m1 plus m2 with an initial velocity of vi. And then after, we have her momentum, m1 v1 final, and the momentum of the gas, m2 v2 final. So the question is, what is v1 final, and is she still moving in the same direction she was initially, or did she reverse direction by shooting her jetpack? Well, what I'm going to do here is just solve it algebraically, as we always do. v1 final is going to be equal to m1 plus m2 times v initial minus m2 v2 final divided by m1. So now we can plug in the values. m1 plus m2 is 71 kilograms. The initial velocity that she had was 2 meters per second. And then we're going to subtract the mass of the gas, m2, which is 1, times the velocity that the gas was shot at, which was 200 meters per second. By the way, when I made up this problem, I did actually look up real values from NASA, so this is a relatively realistic problem. Then we want to divide by m1, which is 70. If you go ahead and calculate that, you should find that v1 final is equal to negative 0.83 meters per second. So again, this is a good example where we couldn't predict, just from looking at the numbers quickly, whether she was still going to the right but just at a slower speed, or whether she actually had her velocity reversed. We now can see that she not only slowed down but actually reversed direction and is now heading in the opposite direction that she was before the problem. Okay. That's it for this video. In our next video, we're going to look at the different types of collisions. We're going to look at elastic and inelastic collisions.